Hello everyone, welcome to this lecture series on probability and statistics. And we have covered a lot of things till now. And today I want to start a new topic, which is counting. And this is a very important topic in the probability space. You must have also heard permutations and combinations, which is essentially the same thing. So, permutations and combination. So, yeah, I will come to what permutation means and what combination means exactly. But you know what counting means, right? We use counting a lot in our day-to-day life. We count a lot of things. Although there's a very sophisticated theory of counting when it comes to mathematics, when it comes to probability, and hence uh, it's important that we actually see the mathematics of it, not just consider it as an English word. So yeah, I would like to start by saying that counting is very often used in probability, like in order to find probability of anything, and most specifically finite sample spaces. So we have done three types of sample spaces: finite, countable, and infinite uncountable sample spaces. But if you look at finite sample spaces, this is where counting is most relevant. But there are n number of ways in which you can count different things based on what is being asked. So it is often uh, used to find probability. And one example, which I can directly talk of, is, for example, there is a lottery and a person comes and he has to pick six numbers from 1 to 44. And the winning number is decided by randomly selecting six numbers from 44. Now, if I say you have to decide or you have to think like what are your chances, and by chances I mean what is your probability of winning this particular lottery. It is important that you know what all cases are actually possible, right? Whenever you find the probability of something, uh, depending on whatever chances are there, depending on whatever possible cases are there, that's when you can say what is your chance of winning, right? So, to get your chances of winning, it is important to crack all possible cases. That is the different combination of six numbers that can come up if I talk about this lottery system. So that is why counting is like the backbone of probability. All right. And there is one particular theorem of counting which is very important when we before we get into actual counting problems or actual permutations and combinations. So for any counting problem, we can break them into a series of simple tasks that are easy to count and then use known rules to combine these tasks. So, so what this means is essentially any task, don't consider it as a full problem. Like I'm giving you, okay, count the number of cases, and you like take it as a whole problem. Most most of the times, you can break them down into different set of smaller problems, and then using certain rules, you can combine to find the total count. That's when fundamental theorem of counting comes into play. So suppose you have a counting job and it has k separate tasks and 1, 2, 3, 4 till k. And task 1, task 1 takes can be done in N1 ways. Task 2 can be done in N2 ways. Task 3 can be done in N3 ways, like that. Then the entire job can be done in N1 into N2 into uh, N dot 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 like into NK ways. So like if k is 3, and in that case n1 into n2 into n3. These are the number these these are the number of ways in which this entire task can be done. And to give you a very simple example, Suppose I have three tasks. Okay. Like suppose I have to select three subjects. Subject one, subject two, and subject three. All right. And I have five options in subject one. I have two options in subject two. Okay, let's focus on one and two for now. All right. So I can choose five options in subject one out of the five options in subject one, and one of the two options in subject two. So the total number of subject one and subject two combinations which I can take up is actually 5 into 2, which is 10. This is what this theorem is saying. And to prove this, we have a very easy proof, which is by the mathematical induction, uh, which I can just discuss here. So, just for people who don't know what is mathematical induction, it's a way of proving certain theorems. And what it means is, how we prove is that first is we prove for n equal to two cases. Okay, so that means if I have two tasks, okay, instead of k separate tasks, my k is two. So I have like the subject example I gave, right? So I have task one and I have task two, and this can be taken in can be done in n1 ways, and this can be done in n2 ways. Okay. Now, suppose task one, we know that task one can be done in n1 ways, right? And each of the way I choose, like suppose the N1 way is way 1, way 2, way 3 till way N1. Okay. Each of these, like each of the choices I make, there are N2 new choices which I can make for each of the choices I make here, right? So for the N1 ways in which I have, there are N2 choices for each of the N1 ways. So this is actually N1, N2, N2. So this is true for n equal to 2. And in induction, we assume theorem is true for n equal to k and prove it's true for n equal to k plus 1, assuming that it is true for n equal to k. If we are able to prove this, then we can say that by the principle of mathematical induction, this theorem is proved. So the mathematical induction theorem says that first you prove for n is equal to 2, then you assume it is true for n is equal to k, and then prove that it's true for n equal to k plus 1 using the fact that it is true for n equal to k. If you are able to do that end to end, that means that this theorem is true. And for this particular theorem, this is actually very easy to do. You can try this. I'll add the proof in the caption, but you can try this on your end as well. That is all this theorem says. But this theorem is not sufficient or enough to solve all counting problems, although it is the fundamental for everything. But there are two nuances in this principle of counting. Whenever you are counting, there are two questions you should ask. Are we counting with or without replacement? And whether the ordering of the task is important or not. Like if, for example, in the subject case, I say that I choose out of the five subjects in subject one and out of the two subjects in subject two. The order in which I choose, does it matter? Or can I choose two same subjects? Something like that. So these are the questions you should answer based on whatever task you have been given. So in the next, I'll stop here. In the next lecture, I will give you an example of all these possible cases which are there. There are four cases, right? With counting, so with replacement ordered, without replacement ordered, with replacement unordered, without replacement unordered. So we will take one example and suppose that same question is being asked in four different ways, which are mentioned here. We'll try to find the total count or the total possible cases for each of those. So for now, thank you all. Please let me know if you have any feedback. I will try to include it in the upcoming lecture.